Perfect. Well, hello, everyone. Good afternoon, good evening to all of you. I am Eduardo Serpa, and I am the chair of this second talk today. I'm very happy for introducing Carlos Castro from Universidad Politécnica de Madrid in Spain, where Carlos got his PhD from Universidad Complutense de Madrid in 1997. Working with Enrique Suazua, and then he held a postdoc position in Paris working with Grégoire Allaire. Yeah. And as far as I know, maybe you can correct me, Carlos, you are at Universidad Politécnica Madrid since 2000.
Yeah, that's correct.
Yeah, that's correct. He has studied some mathematical objects like waves, beams, and different properties as homogenization, control, optimal design, and the approximation of control properties by means of semi-discrete system and all that topics. More recently, he has been working on inverse problem and scattering, and that's the topic of today's talk. The title is the Born approximation in the reconstruction in the Calderon inverse problem. So Carlos, please go ahead.
Okay, thank you very much, Eduardo, for your kind introduction. So, well, thank you very much to the organizers, to Ana, to Juan. I congratulate you for this initiative, which is very, very, very good for people, especially for all of us that we are not always have the opportunity to hear people in different areas talking about the most recent research. So this is what I'm going to talk is work that we started in here in the university, in our university, together with Juan Antonio Barceló, Fabricio Maciá, Cristóbal Meroño, and more recently Daniel Sánchez Mendoza. So we started to a new program from zero on the Calderon inverse problem. And well, we have found some results, and I'm going to talk you a little bit about these results. So let me first introduce you what is the problem, what is the Calderon problem. So this picture is taken from the Wikipedia, and it simulates like a cross section of a body. So you can have here some organs, or this can be the lumps or whatever. And the idea is just to try to derive what is inside the body, just with something that do not enters in the body. So it's an indirect method. So one of these indirect methods is the electrical impedance tomography, where you include some current between 2 points. So you put a current here between these 2 points. So the electrons go from one to the other part, and through different paths. These paths are the streamlines of the electric field. And these black lines are the equipotential lines of the potential field, electric field. So they are orthogonal. The streamlines are orthogonal, and the streamlines that are the paths that takes the electrons depend on the conductivity inside. So depending on what is inside the body, they take one path or another. And this, in particular, the configuration of when you put this current, the configuration of the electric potential, which in the boundary, is different. It's different if you have one object here inside or another. Then this configuration in the boundary is different. So the idea is to know the interior just from the relation between the current, the current that you put in two different parts of the boundary, or that you impose, and the relation between this current and this potential field at the boundary. Okay, so from this relation, you put some measurements here or some devices to measure what is the electrical potential here, and you put the current, and from the current you have a configuration of the electrical potential, and you want to derive from this information coming from the boundary of the object, you want to derive what is inside. This is the idea of this electrical impedance tomography. So the mathematical statement of the problem is as follows. For the electrical field, you have the elliptic equation here, where with a coefficient here, which is the conductivity inside the domain. This is a function gamma, which is typically unknown. And what you have is information coming from the boundary. What is the information that you have is the relation between the potential and the current, basically. So here we have written this relation as a function that for each potential gives you a current. In general, in applications, it is the opposite. You put a current and then you measure the potential. But from the mathematical point of view, the problem is very similar, and it is basically to look at the inverse of this function. So, well, let's take in this way because it is more usual in the literature the problem in this form. So the idea is then to derive gamma from this relation between potential and current at the boundary. Okay? Of course, you never have all this map because you don't have any possible current or any possible potential, and you can measure any possible current derived by this potential. So you have some specific data for the actuators that you put or for the sensors that you locate in a problem. But from the mathematical point of view, you can think in this problem in a well, ideal form where you know all the map. So the reconstruction problem is to find gamma from this map. This is what is known as the Calderon problem because he was the first that stated the problem in this way. So this is another way, the mathematical formulation of the problem. You have information on the boundary, and you want to know what is inside. In general, as I have told you, you don't have information in every part of the boundary. You only have some sensors in some places where you can measure the potential, and you have only some places where you put the current. So you cannot have you don't have complete information of this functional. But well, we are going to focus on this problem where everything is known. So there is an equivalent problem that will appear along the lecture. So I will just put it here at the beginning, which is instead of having the unknown in the principal part of the operator, you can put it in a potential. So it's the same problem. You have the same question. If you can derive from the information coming from this boundary, this function that for each f gives you the normal derivative, if you can derive, assume that you know this map, if you can derive this potential. So maybe the physics behind this is not so clear what are the interests, but well, maybe in quantum mechanics or whatever, there are some interests. But in our case, it's just a related problem that it is in fact equivalent to the previous one because there is a change of variables that transform this one in the previous one as soon as the conductivity is sufficiently smooth. In particular, this change of variable requires that you need to do two derivatives of gamma. So at least gamma must be have two derivatives in order to pass from the previous problem to this one. But we can think in a case where everything is nice and both problems are equivalent. So the first question when you have a problem like this is if the problem is well posed. So is this true that this map lambda gamma, this Dirichlet to Neumann map, this information from the boundary determines what it is inside. So, well, this problem has been studied for a lot of people, and the first maybe that they found a positive answer was in 87, Sylvester and Ullman, for dimension d greater than 3. And later in 96 for dimension d equal to for gamma in C2. Later on, people have tried to find a similar result for low regularity coefficients. Well, there are some other works later. Another important thing is the stability. So what is the stability? The stability means that if you have two Dirichlet to Neumann, maybe I can go back here at the beginning. Imagine that you have two very close configurations here of the potential. Then can these two configurations that are very close can be corresponded to very different configuration inside? Because if this is the case, then, well, the information that you obtain from the boundary can be very unstable in the sense that it's going to be difficult to distinguish between the two configurations inside. So this is the stability. If inside. So, well, it turns out that the stability is very bad. So there is a stability, but it is of the logarithmic type. So it is very bad. So this was the first proof in 88. And maybe the work that people most cite in this context is the work of Mandache, where he proves that it is proved that the optimality of this log stability. So there is another important feature here, not only the stability, but the fact that the range of the Dirichlet to Neumann map is a very unknown object. So in fact, you can be very close. You can have two maps that are very close, but this one comes from a potential or a conductivity, but the other, which is very close, doesn't correspond to any conductivity or any potential in this case. So this makes also the problem very challenging when you try to do reconstruction in this setting. So let's talk about the reconstruction methods. What is the ideas that have tried people in this context? Well, the most natural idea is an iterative method based on a least square approach. This was analyzed in the 90s, and the idea is not very complicated. You consider gamma conductivity. You approach by a finite number of numbers. So how you do that? Well, you introduce a basis, for instance, and take the coefficients, or you put a finite element approximation and then consider the values as some points in the interior. Whatever you can find an approximation by a finite number of points. And you can do the same for the Dirichlet to Neumann map. This is a map, so instead a finite number of or a vector of numbers, you are going to have a matrix, because it gives you the approximation of a map is now a matrix. So you can find this, you can project the problem in a finite dimensional space by choosing a suitable basis. And then you can approximate gamma, the conductivity, just by minimizing this functional where you want to compute the gamma star associated to the known Dirichlet to Neumann in this way. So this is the typical least squares approximation that usually requires regularization term. So this regularization 10 is typically Tikhonov, like in the case of this paper, or total variation that has been tried later. This is the most natural approach for this for this problem. But due to the lack of stability, this is quite challenging, and this regularization must be very well chosen and makes this approach usually slow. It's not very bad, but usually is slow. And there is another method, which is the direct method that is based on the theoretical work where the unicity was proved, that use what they are called CGO solutions. I'm not going to focus very much on that, but I will give you an idea because our work comes from this direct approach. So the idea is that from the Dirichlet to Neumann map of a conductivity gamma and the Dirichlet to Neumann map of the associated to the conductivity that it is constant 1 everywhere. So from these two Dirichlet to Neumann, this is usual. This is assumed known. This is the known data. You want to recover gamma. And this is usually known because this is the Dirichlet to Neumann associated when gamma is equal to 1. So from this, you define some functions in the boundary of the domain. So these functions are what are called the CGO solution, that are solution of this equation. This is an integral equation, which is implicit here because the solution appears in the integral and outside. Here there is a green function. I'm not going to talk a lot about that. And here this is a capital lambda 1. This is this operator. So this is something that depends on that. So from this, this is an integral in the boundary. So this gives you a function in the boundary that depends on a parameter. Okay. Then from this, you compute what it is called the scattering transform, which is this integral. Okay. Well, once you solve this, you plug it here. Then you make this parameter theta goes to infinity, and then you invert the Fourier transform. This hat here is the Fourier transform. So you have to invert the Fourier transform, and then you obtain Q. And from Q, you obtain gamma because there is a change of variables that gives you Q from gamma. Well, this is basically the idea of this direct method. And in another, well, the problem with this method is it requires a lot of effort because you have to solve in particular this integral equation. This is a difficult thing, and you have to do this limit. So what they suggested in this paper also was that instead of computing this solution, we are going to linearize this problem. And how we linearize this problem? Well, this part is linear. This part is non-linear because you have lambda gamma minus lambda 1, and this depends on lambda gamma minus lambda 1. So we have to make this that this doesn't depend on lambda gamma minus lambda 1. Then you remove this part here. Oh, sorry. Remove this part, take only this. So this exponential, remove this, then plug this here, and then you have something linear. And then this is a linearization. And hopefully you think that this is going to work. Well, they did some experiment and it worked quite well. So what we did is just to study this object that they found as this linearization in order to approach this problem. So this is basically the outline. I try to, the idea is to try to find a different expression for this approximation, which is called no-Born approximation in 3D. Then we see how we can obtain reconstruction with a fixed point algorithm from this linearization. And then we talk a little bit about what are the difficulties when you try to use neural networks and how this approach of linearizing is helpful in this context. And then, well, if I have time, I will talk a little bit about the generalization to the non-radial case, which is more interesting. So we started with a radial case, which is simpler, but we are extending now everything to the non-radial case. So this is the starting point. This is the linearization that found these authors in 2011. And well, they have some inconvenience. First, you need, it is completely formal because you remove one term from the system of equations before, and it's completely formal. It requires a limit that it is difficult to compute numerically. And they found that they only can compute the Fourier transform for frequencies lower than 30. And they didn't know why this was a limit. So this was a characteristic of the method. So in practice, you only find the Fourier transform for frequencies lower than 30. So what you find is like a Fourier series with a finite number of terms. So this is a low-pass filter. And you cannot determine many details with this low-pass filter. So, well, let's go to this problem and let's focus on the radial conductivity. In the radial conductivity, we are thinking in an object like this that now can be represented by a function in one single variable, which is from the 0, which is the center, to 1, which is the boundary. Okay. So the interesting thing in the case of radial conductivities is that the spherical harmonics are eigenfunctions of the Dirichlet to Neumann map. So, well, remind that the Dirichlet to Neumann map lives here in the boundary. So the spherical in the dimension equal to this is basically the sinus in cosinus, and these are eigenfunctions of the Dirichlet to Neumann map. And in fact, the Dirichlet to Neumann map is diagonal in this basis. So this is a good thing. The bad thing is that these diagonal terms, the eigenvalues, are very close to those of the Dirichlet to Neumann map when gamma is equal to 1, which is given by k. So this is so close that it is exponentially close. This is bad. Why this is bad? Because the information coming from here is so close to the case of gamma equal to 1 that it is exponentially close. So here is almost indistinguishable. They are almost the same here. This matrix is going to be almost the same for gamma equal to 1 that for any other gamma. So the information, the only practical information is in some very few eigenvalues. And another good point here is that you can compute these eigenvalues for piecewise constant conductivities. In particular, for such conductivity, remind you, this is the origin and this is the boundary now. For this constant coefficient, you can compute the eigenvalues, and you can see how 100 eigenvalues are of the order of 10 to minus 20, more or less. So the power of the usual computers is about, in standard precision, is 10 to the power minus 16, which gives you only 60 eigenvalues. The other ones can be computed only with more precision machine numbers. So, well, something similar can be done for a smooth conductivities, just by approximating the by constant piecewise constant functions. So this is the problem. This is the first theorem we proved. It is this one. This is the gamma S is the Born approximation. So the Born approximation minus 1, the Fourier transform. This is what the definition that found in this previous paper. And what we found is that this can be written in this series. So this may be a little surprising, but it is not so surprising. Why? Because what we did here is just to these exponentials, you put it in a power series. So the exponential, you can put it in a power series. And the power series at the boundary are exactly the spherical harmonics. The spherical harmonics are the eigenfunctions of these operators. So it is not surprising that this appears here. And it is not surprising that the sum appears, and it is not surprising that the powers of this exponential appears. What it is more surprising is that the parameter theta doesn't appear here. And in fact, this quantity doesn't depend on this parameter. And then this limit is not necessary because you don't have to do it. So we find a very nice expression for the Born approximation. So, well, now here again, the problem here is that these numbers are very small, exponentially small, and so to implement this numerically is challenging because you are making a sum of, this is an alternating series where these numbers are very small. So this is something challenging. And in fact, if you try to do this directly, you find that this limit of C equal of 30 is exactly the limit where you can compute this series accurately with a standard precision. Well, in terms of moments, we have something, a very similar formula. So this is something, this is an observation we did, is that if you make just the Fourier transform of gamma minus 1, then this is the definition of the Fourier transform, and you make the same trick, just put this in power series, then you have the series, and then what appears here is going to be, this integral is going to enter in the power series, and then you are going to have something which are the moments of this function. So it's the same formula that before, but now instead of the Dirichlet-to information, we have the moments. So, well, this is interesting because it allows us to use this idea in order to derive the similar formulas for other cases. We can try to find a formula with the moments, and then just replace the moment with the Dirichlet-to information. Okay, because what we prove is that this Dirichlet-to information is very close to the moments in this context. So there is another interesting thing here, is that we have somehow factorized the problem into a linear, very ill-posed problem, because the problem of computing a function from the moments is a well-known ill-posed problem. So this part of the problem, the computing the Born approximation, is an ill-posed problem. While the other part, from the Born approximation to compute gamma, is non-linear. This is linear ill-posed. It is non-linear, but it is stable. It's not ill-posed. So you have factorized in some way the problem in a bad part, but it is linear, and a good part, which is non-linear. So here I did some experiment, or we did some experiment just to compute what is the how it is the Born approximation. So this is a conductivity which is piecewise constant, and this is what we find as the Born approximation. And this is another example. These are the Fourier transform of the Born approximation and the potential. So I'm going to go faster. We found some interesting features here. For instance, the fact that if three different conductivities are the same until one point close to the boundary, and then they differ, then the Born approximation are exactly the same, but they become different when the conductivities are different. So we found some interesting features of the Born approximation with our method. I'm going to, these are more experiments we did with a singular conductivity also. We found the Born approximation some oscillations. And we also did some experiments similar, well, considering a lot of conductivities. We make a lot of random conductivities, and then we prove what was the difference between the Born approximation and the conductivity. And we find that the difference depends on the radius. Close to the boundary, they are very close. This is 10 to the power minus 1.5. But when you go inside the domain, you are farther from the boundary, then the errors are more and more algorithmic. So the Born approximation usually is a good approximation close to the boundary. So we also work in a fixed point algorithm to recover the nonlinear problem. Yes, this is a typical fixed point algorithm that you approximate the nonlinear with a linearization. So we did this fixed point algorithm. I'm going to, maybe I'm a little bit short of time, so I'm going a little faster in this part. So these are some error also estimates on the Born approximation with discontinuous and discontinuous and smooth conductivities. So the Born approximation is quite good, especially when we are close to the boundary, but and it can be improved with this iterative fixed point algorithm. Let me just, as we were talking about in the previous lecture about neural networks, what happens if we try to solve this problem with neural networks? So we can do something very naive. You can put some, in this case, instead of conductivities are potential, but it is an equivalent problem. So you have some problems, some potentials. You discretize this potential with some, for instance, Fourier coefficients. You make the same thing with the Dirichlet-Neumann map. And as they are radial functions, you can characterize them by the eigenvalues or the diagonal of the matrix. And then we compute a large databases of potentials and Dirichlet-Neumann data. And then you want to do to reconstruct with a neural network something that relates the conductivity or the potentials with the data. Okay, so we try, for instance, an ODE that tries to find path between the potentials and the Dirichlet-Neumann map. Well, we have tried a neural ODE. I'm going to skip this part. But the idea is just here it is a picture of the potential. These are the first two Fourier coefficients of the potential, and this is the first two eigenvalues of lambda cube. So you can see that the picture is very different. So these are very dispersed, and these are very, very concentrated. If you try to do a neural network that assigns or that tries to identify each red point with a blue point, then you find difficulties because there are very close blue points that must go to very far away red points. So this is a very difficult problem for the neural network because information is so compressed that it is very difficult to go back. This is the typical situation in an ill-posed problem. So, for instance, when you try to do this, this is the real conductivity, and this is what the neural network finds. It's not so good. Here is another example. So, a second approach is, well, as the linear part, which is the ill-posed part, let's try to make the neural network just learn the nonlinear part, which is stable. Then things are much better. Don't remember that there is an ill-posed problem, which is linear, and a nonlinear, which is stable. So let's try the neural network in this part. And this is, we are going to use our formula that allows us to find this Born approximation. So, and then things go much better. So now the set of points are more similar. This is the Fourier coefficient of the Born approximation and the Fourier coefficients of the real potential. So they are not so dispersed. They are also they have similar structure, and for the neural network, it's much better to find them. So here, for instance, we have the real is in blue, and in red is what find the new strategy, and this is the Born approximation. So we did some experiments. We tried to compute the error with 1,000 different potentials, and well, we find that with the machine learning naive, the first one, the error is larger when you are close to the boundary, but it is better than the Born approximation close to the center. While when you consider the second method, the one that only try to learn from the Born approximation, then the error is smaller than the Born approximation and smaller than the previous machine learning technique. Okay, so just to finish, just to tell you that we did this for the radial case, but this gave us the clue to attack the non-radial case, and this is what we did. We are doing now. We are working in the non-radial case, and we tried the same thing. We found a similar formula for the non-radial case. Here are the eigenvalues of the Dirichlet to Neumann map, which is no longer diagonal, so there are two indexes here. And then, well, this is the expression that we found now. This is the information coming from the Dirichlet to Neumann map. So the formula we obtain is obtained in the other thing. So with the other strategy, we found the formula for the moments, and then we found that the moments are close to the Dirichlet to Neumann data, and then we just replace the moments by the Dirichlet to Neumann data, and this is the formula that we obtained. So this is basically the idea. And this is a theorem that we proved. And this is a very preliminary picture where we consider a non-radial potential. This is the case of the potential, and this is the section, and this is the potential and the Born approximation, which is quite close. We have some problems here because now the Dirichlet problem is not so easy to compute because we have to solve this elliptic equation for a non-radial conductivity, and there are not explicit formulas like in the case of the radial conductivity. We have to use some finite element or whatever. Here we are using polynomial spectral approximation because it is more accurate. And we have some problems to find the Dirichlet to Neumann map, to solve the Dirichlet problem in order to solve to use this formula. But well, this is something that we are working now in the non-radial case. We have some promising results for the moment, and we hope to have something better in the future. So some conclusions. Maybe I have, well, I just will give some, I'm going to read very fast then. We have deduced a new formula for the Born approximation that it was a tool that was known for the three-dimensional case. And this formula recovers the Fourier, the Born approximation as a series instead of a problem that requires an integral on the boundary with a limit, and it was much more complicated. And there is an analogy with a similar formula for the moments, and this allows us to generalize this idea to other cases, like in the non-radial case. And we require large precision for this implementation. We recover from the Born approximation fairly well the conductivity, especially in the boundary and when it is not very different from one. But the fixed point iteration is quite effective in order to go further in the approximation. Well, we are working on new formal reconstruction using this Born approximation with this idea of the series. Well, I'm going to stop here. Thank you very much for your attention.
Thank you, Carlos, for this nice talk. Thank you very much. And we open up for questions from the audience.
Yes, can I ask something?
Yes,
Yeah,
Paco,
please.
tell me.
Okay, Carlos, thank you for the talk. I'd like to ask you about your machine learning simulations, because
Yeah.
the tendency is correct. You know, you said that the approximation is not good whatsoever, but the tendency is correct.
Yeah,
So
it's surprisingly.
I wonder, is the problem is that you don't have enough data, or the calibration of the network? Do you have pictures for the loss history of the
No,
optimization algorithm?
no, I cannot show you. Well, I have them, but I don't have it on hand now. I can send it to you. But yeah, we didn't work very much on that, Paco, because of this picture. So you can see here, no, the machine learning tried to associate blue points, which are the Dirichlet to Neumann map, with red points. So you can see that there is really a very different structure. And even you find that very close, here you can see here, for instance, these are very close blue points that goes to very far away. So it is difficult to
Yeah.
imagine that something like a based only on the data can accurately approximate this problem. So
I see.
maybe
Yeah.
we didn't pursue sufficiently because we were a little discouraged because of this picture, but maybe we can try harder. I don't know.
Yeah, I recommend to push forward to this problem,
Yeah.
because I'm
You
sure that
think there is a hope here?
Yeah, I think so. Yeah, sure.
Well, it's not. Well, I said it's bad, but you can see it's not so well. This is the reconstruction that you. So
Well,
some features are found.
the tendency is correct. That's
The
true.
tendency is correct. Yeah, you
Yeah.
are right.
Anyway,
Well,
okay. Thank you, Carlos.
thank you.
Please, if you have more questions, feel free to ask it directly. Carlos, I have one. Just before you state your first theorem here, you were mentioning that you find this some trouble for frequency higher than 30, no?
Yeah, that's a question which is very also surprising.
But because that was numerically, no? That the observation of that instability for frequency higher than 30.
Is 1 to the power k, and you have when c is of the order of 30. When c is of the order of 30, you have 30 to the power 2k minus 2. So you need, so this is of the order of 10 to the power 16, basically when k is of the order, I don't remember, but it's about 60. About 60, more than 60 terms here are impossible with standard precision. You need more precision. And this is something that you cannot avoid it, because this is an explicit expression, and you cannot. Well, we don't have any idea on how to compute with a standard precision something larger than the Fourier, something like the Fourier transform in an interval which is larger than 33, 34, more or less. 30 is seems to be a limit that we cannot, and we don't know how to, if we can somehow do something with this formula to approximate something which is, it's like the sinus, no? If you try to approximate the sinus, you put a computer sinus of 100 and it gives you the number. and it's correct. But why? Because the sinus is periodic, and you just only have to go to approximate this in minus p pi, in minus pi pi. So this is like, but if you had to do that something, you have to approximate the sinus with the series, with the power series for c equal to 100, you have the same problem, because this is an alternating series with very large numbers divided by very large numbers, and it's difficult to, well, something difficult.
Yeah.
We don't know how to improve that in another way that just using more precision in the computer.
I see. Very nice results anyway, Carlos. Maybe there are some more questions, maybe in the chat, or please feel free to ask. In the chat, no, there's no questions. So, well, if not, Carlos, well, I really thank you for sharing with us your results. Also, thank you to Paco. Okay, and we will have next session of this seminar on January 22 with Oana Pakovniko from the UK and David Ruiz